We just finished talking about functions that are continuous or are not continuous and the rules for continuity. But now let's talk about the different types of discontinuities. So if a function's not continuous, what does it look like? We've got three different scenarios on the screen, and each one of them is one of the classified discontinuities. On the left, we have a removable discontinuity. That's the kind that has a nice smooth-looking function, except for one point has been essentially removed from the curve, and maybe it's been placed somewhere else. So the function is defined, but it just is not continuous because a point has been removed and placed somewhere else. Or we have a jump discontinuity. We can see a jump very clearly because we have a nice, smooth, continuous line. All of a sudden it disappears, makes a huge jump, and then continues on continuously. So we have a jump discontinuity here in the middle. And then on the right, we have what's called an infinite discontinuity. This is where the vertical asymptotes happen. We can see that it's not quite a jump discontinuity because it's not just a small jump from one side of the function to the other. It shoots all the way up to infinity on either side, so that would be an infinite discontinuity. The formal definitions for each of these, we have the removable discontinuity. Formally, we say that a function would have a removable discontinuity if the limit exists, but maybe the other two conditions are not met. So the limit exists, but the function is not equal to the limit at the point that we're approaching, just like we saw where the hole had been removed from the function. So there was like this big hole and it had been moved somewhere else. Something to consider here, when we say that the limit exists, what we mean is that the limit's equal to a real number, not infinite. So we would need the limit to be equal to something like 4 or 2 halves. 2 halves. I really just said that. 1 half or 3 halves or any fraction you could think of. So if the limit exists, it's equal to a real number, but maybe the function definition doesn't match the limit that you calculate, then we would call that a removable discontinuity. For a jump discontinuity, we formally define that by saying the left-sided limit and the right-sided limit both exists. They're not infinite either. They're both equal to a real number, but the left and the right limits are not equal to each other. So that's the case where we saw a jump in our function. Lastly, we have the infinite discontinuity. This would be where the left limit is infinite or the right limit is infinite. Now it's possible that both the left and the right limits are infinite. Maybe they both go to infinity. Maybe they both go to negative infinity. We would still call this an infinite discontinuity because even though maybe they're both going up to positive infinity, I can't draw that without picking up my pen because it goes all the way up and it never crosses that dashed line, so I would have to pick it up and then bring it back down. So it's not possible to have infinite limits and then be continuous at that point. It's a discontinuity. So there we have it. We have our three discontinuities: removable, jump, and infinite. And now we're going to practice classifying those discontinuities algebraically. Let's revisit our discontinuous function from earlier. We know that this function is not continuous. It failed the three continuity conditions. And we can see that it's not continuous looking at the graph. But if we don't have a graph and we didn't already know that it failed the three conditions, how could we classify the type of discontinuity? Well, we need to look at our function and suspect what type of discontinuities we could have. It's not a piecewise function, so it's very unlikely that it could have a jump. Jumps are caused by a switch in the definition of a function, so probably not a jump. So it's either a removable or an infinite discontinuity. In both of those cases, we can prove that it's discontinuous by looking at the limits. So let's start off by looking at the limit, where x is approaching 2 for our function. If we try and plug 2 in directly, we do end up with an indeterminate form. But in the last section, we learned how to deal with that. We said if it's a rational function, polynomial on top, polynomial on bottom, we should try and factor it completely. And then simplify. So in my numerator, I have a difference of squares, which looks like x plus 2 times x minus 2 when we factor it. The denominator is only one set of terms. I can't factor that any more than it already is. They have no common factors. But the good news is that I can see my numerator and my denominator have a matching factor of x minus 2. So since any number divided by itself is equal to 1, I can simplify those off, leaving behind x plus 2. Now technically that is not the same function we started with, but if you remember, this process tells you find a function that's similar enough that they share all of the same points except for the point at x equals 2. Now we can replace the function that we started with this twin function and then evaluate using direct substitution. We get 2 plus 2, the output is 4. In this case, the limit is equal to a real number, which means we know we don't have an infinite discontinuity. It has to be removable. And we can tell that it's removable because the limit is approaching 4, but the function itself doesn't even exist there. So my function evaluated at x equals 2 does not exist because it's undefined. We know we have a removable discontinuity at x equals 2. So when it's time to classify discontinuities in your homework, this is going to be a bit difficult to do in the online program, but this is the work that you're going to show. You're going to go through this process of eliminating which of the discontinuities you cannot have, and then you're going to use a limit, in this case, to show that the limit does exist, it's equal to a real number, but it's not equal to the function output at that point. And let's revisit the second function we looked at, which was a piecewise function. We know that it's discontinuous. We saw the jump that's happening here. But again, what would we do if all we were given was the function and we weren't able to graph it? Could we classify this as removable, jump, or infinite? Now looking at our function, we know that we're approaching the x value that switches the definition in our piecewise. So we should be very suspicious that we could have a jump discontinuity. In order to classify if it is a jump discontinuity, we need to look at the left limit and the right limit. So let's go ahead and look at each one. If we're coming from the left, then remember that the x values that we're using to approach 3 are smaller than 3, which means f of x is going to be replaced with the top definition in the piecewise function. And then we'll evaluate that using direct substitution. And then we'll move down to the right limit. If we are letting x approach 3 from the right, then the x values that we're approaching 3 with are bigger than 3. So we'll have to use the bottom definition of our piecewise for this limit. And then we use direct substitution to evaluate this limit. And we get 4. We just did the left and the right limit, and we need to decide if we have a removable jump or infinite discontinuity. I suspected it was a jump discontinuity because we're looking at a piecewise function. So we found the left limit and the right limit. Now, if this were a removable discontinuity, then the two-sided limit would have to exist. We can see that this is not a removable discontinuity because our left and right limits don't match, which means the two-sided limit doesn't exist. Since these guys don't match, the two-sided limit does not exist. So we know it's not a removable discontinuity. That leaves us to check if it's jump or infinite. If it were an infinite discontinuity, then the left limit or the right limit would have to be infinite. But neither one of these are infinities. So we know that they're equal to real numbers, not infinite, which leaves the only possibility would be a jump. Now the last thing we need to do, now that we've eliminated infinite and removable as our discontinuity choices, we need to make sure that it definitely is a jump discontinuity. And if we look back at our definition for jump, it says that the left limit and the right limit are equal to real numbers. These are both real numbers, but they're not equal to each other. If the left limit and right limit are not equal, but they're real numbers, then we know that we have a jump discontinuity. Let's take a look at a new function, one that we haven't worked with before. In this case, I have a rational expression, x plus 2 on top, x plus 1 on bottom. We want to know if it's continuous at x equals -1. And then we want to know if it isn't continuous, if it's discontinuous, can we classify the discontinuity? So let's go through the 3 continuity conditions. First condition, is the function defined at -1? So we go and we try to plug it in using direct substitution. Whoops, we want to replace our x's with -1. In the numerator, we have 1. In the denominator, we have 0, which is not a real number. Therefore, this is not defined. Since the first condition failed, we know that this function is not continuous. Now that we know it's not continuous, we're going to switch gears, and instead of checking if it's continuous, we're going to classify the type of discontinuity. It's either removable, jump, or infinite. Now, we've eliminated some possibilities in the last functions. Let's try that here. If we suspect it's a jump, then we need to kind of think about what would cause that to jump. I don't see a piecewise. I don't see a flip in the way that the function's defined, so likely it's not a jump. That means it's either a removable or an infinite discontinuity. So we're going to look at the limit as x approaches -1 so that we can decide if it's removable or infinite. Looking at this limit, if I try to plug in x approaches -1, I get indeterminate form. With indeterminate forms, we have a few tools we can use. We can try and factor it, but that expression cannot be factored. We could try a conjugate, but there's no radicals here, so a conjugate's not going to help either. We can try simplifying the complex fraction, but this is not a complex fraction, so that's not going to help us either. Instead, we have to remember that some limits are equal to the form a number divided by 0. I'm using k over 0 because that's what our textbook uses. And if we look back to the part of the continuity rules that we checked, we did have a number on top and 0 on bottom. For any limits that have the form a number on top, 0 on bottom, what we did was we used some of the shortcuts where we rewrote the expression kind of like this, and we decided what type of limits we had based on the exponent. So we're going to factor our expression so that it looks like x plus 2 over 1 times 1 over x plus 1. And then I'm going to use my limit laws to separate the limit into two pieces. Because we have a product when we factored it, we're able to separate the limits into two different limits. The first limit doesn't have any kind of problems with it. I plug in -1 and that works out to be +1. The second limit, however, as x approaches -1, this turns into a 0 in the denominator. So if I look back to our shortcut for limits of the form number divided by 0, we said that there's two options, either n is even or n is odd. N is the exponent in the denominator. Technically, we don't have one, which means that it's like an exponent of 1. 1 is an odd number. If the exponent was odd, then we know that we have infinite limits that are going in the opposite direction of each other. To figure out if we have positive infinity or negative infinity or does not exist, we're going to need to separate this into two one-sided limits. For the left limit, x is approaching -1 from the left. That means we're using numbers that are less than -1. If we're plugging numbers that are smaller than -1 into this expression, then I have a like -2 plus 1 in the denominator. Remember, -2 is smaller than -1 because it's further down the number line to the left. If I were to plug numbers smaller than -1 in, I would get negative infinity coming from the left. And because that exponent is odd, I know that my right-sided limit would have the opposite sign. But we can verify that if we like. If x is approaching -1 from the right, then we're using x values that are larger than -1. So that would be something like 0. If I were to plug 0 into that expression for x, I would have 1 divided by 1, which is positive. Remember that we were trying to figure out what this two-sided limit was. And because we had infinity, or rather we had a vertical asymptote caused by the denominator, we had to separate our limit into the left and the right limits. When we did that, we saw that the left limit came out to negative infinity, the right limit came out to positive infinity. These do not equal each other, which is another reason for a discontinuity, but also they're not equal to real numbers, they're equal to infinities, which means we don't have a removable discontinuity, we have an infinite discontinuity. And if we graph that, we can totally see the infinite discontinuity. I have the vertical asymptote at x equals -1 graphed in the orange dashed line, and as we follow our function from the left heading towards that vertical asymptote, we can see that the function values are shooting down to negative infinity. And if we were to come from the right, we would see that as we're heading towards that vertical asymptote, our function values are heading up to positive infinity. So we have infinite discontinuity here.